Exercise 7E. Combinations. Combinations is in contrast to permutations. Now remember, permutations was the number of ways that you can arrange something where order matters. The classic example that I always chose is the first three people here. If I chose a team to, I don't know, let's go for a run, and I chose Michael, Jamie, and Rose, then it doesn't matter if I chose Jamie first, then Michael, or Michael, then Rose. The team of three is still the same team. I haven't changed anything, it's still the same group. That's called combinations. Whereas permutations will dictate that it does matter who I choose first. Maybe it's because I have some sort of biasness to them. And I'm ranking them. So I'm choosing Michael first, and I'll go with Jamie maybe second, and I go with Rose, one of my left over. Yeah? Then the first, second, third will matter. So that's when order matters. But in terms of the combination, it's still Michael, Jamie, Rose. Okay, so permutations matter which one I choose first. Combinations technically says it's the same group, so you don't count it as a second group. You're like, well, that's one group. There's no difference between shuffling them around, it's still the same group of people. Okay, so that's what combinations mean. So one of the things that we can already see is permutations is the total number of ways you can arrange objects. Combinations is limited because you can't have repetitions, meaning you can't have the same groups. So if you had A, B, C, then C, A, B is still the same thing. That's what combination is trying to say. Whereas permutation will say, no, that's different. Having C, A, B versus A, B, C, those are two different. So you would say you have two ways. Whereas combination would say you only have one way. Okay, so what that tells us, the first thing to understand the formula, is that permutations tells you the total. So out of the total, the combinations will be less. It's always going to be less because combinations has the repetitions. Okay, so keeping that in mind, let's see how we're going to do something like this. Let's say I have, how many ways can two letters be chosen from the set A, B, C, D? So I've got four groups, and I want to choose how many ways I can choose two items. Okay, so I can choose two items. Now the thing what we know is if I've got two boxes, normally if it's permutations, meaning it does matter which letter I choose first, then you would say, well, there are four options to choose in the first one. But after I choose it, I can't choose it again. And therefore I have three left. So you'd say 4 by 3, and you'd say there are 12 ways of possibly figuring this out. Okay, so 12 ways of rearranging A, B, C, D, where you pick only 2 out of the 4. Okay, so effectively all I'm saying is I'm saying 4 out of 4 items, I'm choosing 2. So 4p2, permutations. So this is the formula for exactly 12. It's the same thing. And these two, this is exercise 7, I think it was 7C. 7C, where you choose your items. And we can say, well, 4 by 3, that's the logic. That's our answer using multiplication rule or multiplication principle. Here, we just change the number 12 or 4 by 3 into a formula. Yeah, this is your formula. You got 4 factorial by 4 take over 2 factorial. Yeah, so n minus r factorial, or n factorial over n minus r factorial. This is your formula. But what I want you to understand is the 2 and 1 will cancel and you still have 4 times 3, which is 12. Now this is the total number of ways. Now let's write it out. Let's have a look. When I write it out, these are my 12 combinations. The 3 by 4, that's 12 combinations, which is what I was saying here, 12 ways. I can have AB, maybe not B, I'll switch it to C. I can have AD, so it's AB, AC, AD. Or if I started with B, I have BA, BC, BD. Or if I started with C, I have CA, CB, CD. Or if I started with D, I have DA, DB, DC. So this makes sense. 12 ways in total, right? The ones that I just colored in orange, this talks about, well, actually AB and BA are the same groups. AC and CA are the same groups because they're both the same group. Okay, in terms of order, it doesn't matter. Permutations, combinations. See the difference between the two? So combinations, you can't have BA and AB, they're the same group, so you count it as 1. BC is the same thing as CB. And then you have BD, which is the same thing as DB, and CD is DC. Okay, so that's what I just organizing so you can see. Combinations. How many, just logically, we're coloring it, there's 1, 2, 3, 4, 5, 6. There are 6 combinations if it doesn't matter in terms of, if it doesn't matter about order. Okay, so if order doesn't matter, you can have it CB or BC, it doesn't really matter, that's still counted as 1, and there are 6. If order does matter, which means permutations, then you have 12. That's what I want you to see. Permutation is meant to be your total. So if, let's say, I didn't know the answer was 6, so I'm showing you diagrammatically, we all know the answer is 6 now. There are 6 ways to arrange 4 items and choose 2 where order doesn't matter. So you know the answer is 6, but let's think about it. Let's say we didn't know the answer was 6. Let's C be the number of ways you can arrange where order doesn't matter. Okay, so out of your total, out of your 12, there has to be a certain number of ways where you can order it where it doesn't repeat. Okay, so A, B, and B, A doesn't occur. Right? There has to be a certain number of ways. There could be 2, there could be 3. We know the answer is 6. So let's call it C for now. If we call it C, then what I want you to understand is for every number of ways you have, to make it a total, you're just switching it. So AB, there's 2 slots there. There's AB. What's another way of writing AB is BA. So for every AB, AC, BC, for every one of them, they all have 2 factorial ways of rearranging. Does that make sense? Okay, because I'm choosing 2. If I chose 3, then for every one of those, they would have 3 ways of moving them around. Yeah, because if I had, for example, B, C, D, those are my 3 possible options. How many other ways can I order this where order does matter? See, if order does matter, I can have it as C, B, D. I can have it as B, D, C. I can have it as C, D, B. I can have it as, what else? D, B, C, and D, C, B. True? But all of this is one combination. There are 6 permutations, but 1 combination. Does that make sense? So what I'm trying to say is for every one of these 3 choices I have, there are 3 factorial ways or permutations you can have where order does matter. So what I'm saying in that example there, for every 2 letter that is a combination, they should have 2 factorial ways of arranging them. An example would be if it was AB, the only other way to arrange it is BA. If it was AC, the only other way that you can arrange that is CA. So that's why there's only 2 ways. 2 factorial is 2 by 1. There's only 2 ways of rearranging them. But in terms of combination, AC as a combination, I've got AC and CA. That's the number of permutations, 2 ways. But if I want combinations, only 1. Does that make sense of what I'm trying to say? So what I'm trying to say is this line that comes up next, I wanted you to understand. If the total's 12, this is what I want you to understand. The number of ways that you can arrange it without where the order doesn't matter, if you times it by, for every one of those combinations you have, if you times it by 2 factorial, that's the number of ways you can arrange them, that should give you my total. Sure? Okay, so total number of ways where order doesn't matter, it's limited. And if you took those limited ones and for every one of those combinations you times by 2 different ways of arranging them, then you get the total. And that's what we're doing here. If I've got 2 different ways of getting AB, 2 different ways of getting AC, 2 different ways of getting AD, 2 different ways of getting BC, 2 different ways of getting BD, and 2 different ways of getting CD, I should get 12. Yeah, so 2 plus 2 plus 2 plus 2 plus 2 plus 2, or 2 times 6 is 12. It makes sense. Okay, because that's paired up with this is paired up with that, this is paired up with this is paired up with that. It makes sense. But how do I get that 2? That 2 factorial is based on, because I've got two items I'm choosing. It obviously changes if I had 3. So if I had 3 factorial, it just means for every C, it will be 3 factorial. Yeah? Okay, so why is it important to understand that logic? It's because it's where the formula comes from. So the formula is just saying, well, if you want to find C, the total number of ways to get where order doesn't matter, well then you can rearrange it and say, divide both sides by 2 factorial, and I get C, will equal to 12 divided by 2 factorial, which is 6. And that's true. That's what I had before. It made sense. Just logically, in terms of the diagram, it was 6. How do we feel about that? Okay. I'm using C, but the formula uses something else. But I'm just using C for now so you understand my thought process, why this works. Okay. So let's do another example just so you get a good feel of this. Okay, so same idea. Instead of A, B, C, D before there was 4 items, what if we had now A, B, C, D, E, F, G. So there's 7 items there. Okay. So now, same concept. There are 7 items. Okay, oops. There are 7 items. But what we need to understand is we're choosing 3. So it says we want to count number of ways that 3 students can be chosen from a group. So let's say I've got A, B, C, D, E, F, G, 7 students. All right, but I'm choosing 3. So think of the boxes, you got 3. Okay. Now for every combination, what you have to understand is C is the number of ways where order doesn't matter. For every combination, we picked a random combination, say B, D, E. Okay, so let's say I chose the student B, chose student D, chose student E. Right? Then there are, this is one combination, but how many permutations are there for that? Logically, you can have 3 factorial. There are 3 ways of arranging this, but it's still under the B, D, E combination. Because I can rearrange this to have B, E, D, but that's still the same group of students. It's like me saying before, if I chose Michael, Jamie, and Rose, doesn't matter what order I choose, it's still Michael, Jamie, and Rose. It's still the same combination. So for every combination, every 3 that I can choose, every one combination I have, there are 3 factorial ways of arranging them. Okay. So what we need to understand is, well, that means, what is my total? What is my total? My total would be normally 7. If I have 7 choices, normally you would say out of 7, I've got 7 choices in the first one, then I have 6 in the second one, then I have 5 in the last one. This is my total. This is out of 7, choose 3. That's what that means. Yeah. But out of my total, the problem is order does matter. See, that's why they're repeating. I don't want that. Out of my total, I know that it has to be C amount of combinations where order doesn't matter. Now to make it the total, for every one of those combinations, there should be 3 factorial. For every combination you think of, and the combination I made up before was B, D, E. That's one combination. For that one combination, there are 3 factorial ways. I can choose another combination. I can say A, B, C. So that's another combination. But out of that combination, there's another 3 factorial ways of arranging it. Okay, so there's another factorial of that, and then you can have B, C, D. That's another combination of having 3, but then there are 3 factorials of doing that. That's what I'm trying to say here. For every combination you have, if the answer was 7, then for every 7 one of them, they have 3 factorials. Just like what we did before. Is that making sense? Yeah? And so therefore, if you want to find C, C is just literally saying, find whatever this answer is. 7, choose 3. That's your total. Divided by the number of 3 factorial, that should give you C. Now I'll show you how the formula works now. See, if we do that, here's the logic. There's 7 items. Wait, let me just go. Cool. That shouldn't be right. I've done something wrong. That doesn't work then. It should be 3 boxes. We said that it was 7 by 6 by 5. So that means 7, choose 3 is that answer there. Okay, I'm going to type into my calculator so we get an actual number so we can work with. So 7 by 6 by 5. 7 by 6 by 5 gives me 210. This is my total number of ways where I've got 6 students and I only choose 3. The problem with that is out of those 210, some of the students are the same students. It's the same group. So I'm saying, all right, well, out of the total, to get the total, 210, there has to be C amount of ways where the groups are individualized. Okay, each group is just one group. But I know for every group, there are 3 factorial ways for each group. Okay, and that will give me the total. So for every group, if I times it by 3 factorial, that should give me the total. So if I rearrange it, C should then equal to 210 divided by 3 factorial, which works out to be, what, 210 divided by 6, is it? Yes? 35. Now we know that means there are 35 combinations that you can think of, where you can choose 3 letters and it's just one of itself. So there are 35 ways. See the difference between 2, one has 210, that counts everything. But out of the everything, I only want ones where I just want groups. I want the group of BDE. I want groups of ABC. I want groups of BCD. Okay? There are 35 of those groups there. Now, how does the formula come about? CP3, another way of writing that, which we learned in exercise 7C, is you can write this as 7 factorial over, 7 minus 3 factorial. True? Okay, so this is what we've learned, how to rearrange the 7 factorial, because 7 factorial is 7 times 6 times 5, and you can remove that 4 factorial. That's what that's for. Yeah? So there's 7C, exercise 7C. Now if I replace everything, instead of 210, let's say I wrote that now as 7 factorial over 7 minus 3 factorial. Okay? What did you do afterwards? You said divide both sides by 3 factorial. So this is like me saying, what is 7 factorial, 7 minus 3 factorial, divided by 3 factorial. And this now gives me an answer where you can write C will equal to, when you divide to the reciprocal, so this is why it becomes 7 factorial over 7 minus 3 factorial times over 3 factorial. Yeah, I'm just using basic fractions. So this together gives you the formula for any number of combinations you want. It will be 7 factorial over 7 minus 3 factorial times 3 factorial. Okay? And this means that you can generalize it now. What's 7? 7 is your number of items you have. So you can write here, number of items you have, factorial. Number of items you have, take away how many you're choosing. I'm choosing 3. So it's number of items you have minus 3 factorial times, well, how many are you choosing? Oops, times r factorial equals to C. Now in your textbook, they don't just call it C, it's just a notation, they'll say it's n, choose r. But that meaning means the same thing. It means a C has to be the number of ways that you can arrange it, and this is where your formula is coming from. Okay. So that's what I'm trying to do. I'm trying to get you to understand the difference between, because when you're reading the questions, it's important for you to be able to tell the difference when you use combinations and when you use permutations. The combinations, when the situation, the number of students you choose, the group or the team, doesn't matter. But if I asked you for the number of ways where what it does matter, choosing something like first, second, third does matter, you use permutations. Whereas combinations doesn't matter. And I'll give you some examples so you can see. But does that logic make sense as to why the formula as it is? Yeah? Yeah? All right. Now, what did I do over here? That's all wrong, by the way. So, all this is wrong. All of it, I got to fix that PowerPoint, okay? It's not 5,040. It should have been 210 ways. But anyways, here we go. Let's go to a pizza can have 3 toppings chosen from 9 options. So I'm going to rub this off now. This is from your textbook. A pizza can have 3 toppings. So you've got 3 toppings chosen from 9 options. So there are 9 options that you can choose from, and you only get to choose 3 toppings, right? So how do you know if this is combinations or permutations? Because if I just gave you the question, you have to be able to tell the difference. See, logically, pizza toppings, it doesn't matter which one you choose first. If I chose mushroom, ham, pineapple, it doesn't matter on that pizza, even if I said ham first, pineapple, then mushroom, it's still the same pizza. See, when you order that pizza, it still has mushroom, ham, and pineapple. It doesn't matter which way you choose it. See, permutations would say, no, it does matter. Which one I choose first, that's a different pizza. Okay, maybe in terms of layers, then that will be a different pizza, like having mushroom first, then pineapple, then ham. Okay, maybe the layers will matter if, for whatever reason, the pizza's doing layers. Otherwise, it doesn't matter. So hence you know this is combinations. So how do you answer the question? Same thing again. You already know the general formula. How many items do I have in total? I've got 9 options. How many am I choosing? 3. So answering the question, it'll be 9 factorial, chosen 3, so 3 factorial times 9 minus 3 factorial, and that will give you the answer. Now you can do it 2 ways on your calculator. You literally type just NCR, so type NCR, or you can go to menu, probability, combinations. The first letter or first space or entry is for your total number of options, and 3 is how much you choose, so it's NR. Alternatively, if you just want to type out the whole entire fraction or formula, they're both the same thing. This is quicker, obviously. Okay, so NCR is that, or this is the formula. They both give you 84. How do we feel? Good? All right. Now, in the second example, if you read it, it sounds a bit confusing because a lot of the terminologies we don't understand. It's saying how many subsets of 1, 2, 3 all the way to 20 have exactly 2 elements. All they're trying to say, elements is the number of numbers you have in the set. Subset means group. Okay, so they're saying how many groups can I have where I only have 2 elements, meaning two groups. So I can have 1 and 2. But you see, the group of 1 and 2 doesn't matter if I have 1 and 2 or 2 and 1. It's the same group. It's like saying, if I chose Jamie and Michael, it's a group. Whether I chose Michael and then Jamie, it's still the same group. I haven't changed the group at all. I might have changed the order, but it's still the same group of people. Okay? So that's what this is trying to say. So it's the same concept. How many numbers do I have? 1 to 20, and then I'm choosing 2. Okay, using the same form. Easy? All right. Now let's go with some properties here. Wait, what's this one? I think that's the same thing. What did I? Oh, that's right. Actually, your turn. You try this and you tell me what the answers are. Use your calculators, or you can use whatever it is. But I'm trying to teach a property in this slide here. Find out the answer for me. So there are a group of 6 students. In how many ways can you have a group of 2 students to be selected? See, these 2 students, it doesn't matter which way you choose them, it's still the same 2 students. I want to know groups of. So the key word is group. We can group. We can group 2 students. Group of 2 students. What are we getting, guys? What are our answers? Do NCR, number of students 6, NCR 6, choose 2, or NCR 6, choose 4. What is the answer for NCR 6, 2, and NCR 6, 4? What is that equal to? Do we all get 15? Yeah? Now, it's not by coincidence that both of them are equal to 15. It's kind of like what you did in chapter, I think it was 5, the contrapositive. If you think about it logically, if you chose a group where there are 2 students to be selected, so out of the 6, I'll draw a circle so you can see. If there are 6 students, 1, 2, 3, 4, 5, 6. All right, if you're asking how many ways can you choose 2, whatever that answer is, it's like saying how many four students to be selected, it's how many groups of that. It's the same, it's like complements. It's the same thing. It's a number of ways that you can choose 2 to be selected versus 4, it's the same thing. Number of ways that you can move 2 away, because while you're moving 2, you're moving 4. Think of it that way. And every time you move, if I move this group in between, like, actually I should do that. 1, 2, 3, 4. 3, 4, yeah? If I move this group in between, that's one way to move 2, or alternatively, it's also like saying it's one way to move 4. See what I'm saying? So you can say one way to move 2, or another way you can say is one way to move 4. There's 2 ways of interpreting this information. You can say split this 4 and move this one over there. Or you can say move these groups of 2 over here. See what I'm trying to say? So when you say move 2, it's like saying move 4. When you say move 3, it's like moving 3. It's like the inverse of one another. Yeah? And that's why when you do 6-2 and 6-4, it's the same number of ways. It's just how you're looking at it. It's like saying, well, what's another way of thinking of this? I was thinking of flipping a coin, but it has equal chances, so that doesn't really work. It's like saying, I don't know if this is even relevant. I was thinking like, chances of getting a 6 is 1/6. And then if I said, what's the chances of not getting the complement of 6? I think that's just more confusing. I was just trying to say not getting 5/6, you get 1/6. It's the same. It's like a double negative if you do it that way. Okay. So that's why they're just saying in generally, you can look at this property. You can say if there are 6 items, you choose 2. It's like choosing 4 as well. Moving 2 is like moving 4. They're complements because they both add up to 6. Okay. So when they're saying here NCR. 10 choices, let's say this was 10, and I had 3 here, then the complement to that would be 10, 7. Okay, because if I'm moving 3 items, however I move the 3, it's like moving the 7. 1, 2, 3, 4, 5, 6, 7. Because these are my groups, and I can move the 7 around, or I can move the 3 around. It's how you visualize it. You can say, I'm moving the 3, or you can say, I'm moving the 7. Both of them are the same thing. Every time you move an item, you move this item here, that's like another way of saying that's one way to move the 7 items. So it's really in your wording. That's why 10C3 and 10C7 should give you the same answer. And I gave you an example on this page here where I did a whole bunch of them. I did 8, 5. So if it's 5, complement of 5 plus 3 gives you the 8. These two should be equal, and I tried it. They're both 56. Then I went to 110 and 100. So 110 items and I choose 100. There are 100 ways. I want to know the number of ways it should move around 100. But if you move 100 items, it's the same thing as moving 10 of them. So 100 plus 10, it's like the opposite. Okay, so as you're moving the 100, you're also moving the 10s. So if you're moving the 10s, you can say it's the same thing. It's like saying moving the 10s, moving the 100s, and they're both having exactly the same number of ways. Does that make sense? It's like saying this. If I had actually heads and tails, yeah? And let's say, actually I shouldn't even do that now, right? Let's say I now have TH. There's 2 ways of looking at this. You can either say I moved H to the right, and I get TH. Or you can say I moved tails to the left, but both of them are the same thing. So it doesn't matter which way I look at it, it's sort of they're complements of one another. If I said I moved H to the right, that's one way to move H to get TH. Or you can say, take T and move it to the left. See, both of them say it literally in terms of reading it out, it's different, but the number of ways is the same thing. Both of them result TH, it's just how you perceive it. It's the same thing with 10-3, you can say move 3, but as you're moving 3, you technically could be saying you're moving 7. It's the same thing, it's like this idea. It's like the idea of 2, choose 1. And then if you move 1, you can look at it as saying I'm choosing H to move across, or you can say move tails to the left. Both of them are the same thing. Does that make more sense? Yeah. Okay. So that was a better example, actually. There you go. 7E, combinations. That's all we're doing. So I showed you where the formulas came from. There's a difference between the two. One order does matter, the other one order doesn't matter.